Guys, welcome back. We're going to be having a quick look at momentum and impulse in this topic. Four main sections to cover: what is momentum, what is impulse, conservation of momentum, and elastic and inelastic collisions. So first of all, what is momentum all about? Well, there's two main questions that you'll need to ask or answer if you wanted to know how big an object's momentum is, and that is how big the object is and how fast it's going. So the definition really comes from, or is summed up by the equation: momentum is the product of an object's mass and its velocity. So it basically just means there's a very big difference being tackled by your niece and by the beast, or being bowled at by your little brother and Kagiso Rabada. Okay, so the object's speed and the object's mass are the two things that make up its momentum. Easy as that. Now, because of that, the units that we use for momentum essentially come from the units of the thing that it's made up of. So kgs, meters per second, is the unit that we usually use for momentum. Easy as that. Next little section is impulse. Now, impulse is a little bit more elusive. It doesn't even have a letter of its own. It's kind of defined in terms of other things. So if you're asked to define it, the thing to pick up on is that it is the product of the force acting on an object. Sometimes call it F net, probably the most general way that we talk about it, and the time for which that force acts. So essentially what it's all about is, it's a bounce. It's that moment that a ball bounces off the floor, or a racket hits a ball. It's often a ball sport, golf, rugby, anything like that. It's that impact moment. That's what impulse is all about. And there's kind of the two factors that we've got here right there in the equation. One is the fact that the floor is going to exert a force on that ball, and the fact that the ball is going to be in contact with the floor for a certain amount of time. Very short amount of time, but it is significant. And the bigger the force, or the longer the time, the greater that impulse is going to be. Now, the cause of, the effect of that impulse is that it makes that object change its momentum. Okay, mass is probably going to stay the same, but the velocity is certainly going to change. And so, the other way of considering what impulse is it's the change in momentum of an object. Now, if you want to see where that comes from, I'll show you very quickly. So, all comes from Newton's second law, F net equals ma. A, as you probably know, is the change in velocity per unit time. Sub that in there, we get F net equals m delta v over delta t. You see how that got in there? Okay. Okay, that's looking familiar because we know that p is equal to mv. So m delta v, well, that must be delta p. Okay, so F net equals delta p over delta t. Now that is a very useful little expression, because this, as you probably know, is Newton's second law. That too is an expression for Newton's second law. And that comes up a lot in question papers where they ask, what is the rate of change of momentum? Is the change of momentum over delta t means it's the rate of change of momentum. It is not impulse, it is F net. Impulse is the change in momentum. F net is the rate of change of momentum. And then the last thing that we have to do there is just multiply both sides by t, and there we have it. That is where our formula comes from. So impulse, the ever elusive, is defined in terms of the force and the force acting on an object and the time for which it acts, or in terms of the change in momentum of that object. Okay. Which of course we can expand out. So the last little bit I'll squeeze into this little space down here is we can say, well, the change in momentum is, well, what its final momentum ended up being less the initial momentum that it started with. Those equations are all on your formula sheet. Okay, let's just do a quick example of that so you can sort of see it in context. It doesn't come up that, well, it'll come up probably once in a paper, and it won't come up entirely on its own in a question. It's not a big enough topic. It'll come in conjunction with a velocity or motion question, or perhaps a bigger momentum question. Let's have a quick look at. So I'll look here. It's February, March 2010. Here we are. This is the one I was looking for. February, March 2010. Question number 4, or 1G if you've got an Excel booklet. The bounce of a cricket ball is tested before it is used. The standard test is to drop a ball from a certain height onto a hard surface and then measure how high it bounces. During such a test, a cricket ball, blah, 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 a cricket ball of mass 0.15 kgs is dropped from rest from a certain height and it strikes the floor at a speed of 6.2 meters per second. The ball bounces straight upwards at a velocity of 3.62 meters per second to a height of 0.65 meters, as shown in the diagram below. The effects of air friction can be ignored. You've got a diagram. Define the term impulse in words. Okay, so as I said, if you're asked to define it, you talk about it being it's the force acting on object, the product of the force acting on object times the time for which that force acts. Cool, you can have a look at that in the memo just to double check the wording and so on. This is the one that I wanted to do together with you, is the 4.2, calculate the magnitude of the impulse of the net force applied to the ball during its collision with the floor. Now, I hope you printed this out so you can read with me, otherwise it's a bit of a blur, I can imagine. Let's just retrack some of the most important pieces of information and draw ourselves a diagram, because diagrams are awesome. Okay, so here's our object, the ball, 0.15 kgs, we're told, so we can just write that for our mental sake. And ball comes in and bounces off the floor to a height of 0.65 meters, we're told. We're also told that the velocity coming in is 6.2 meters per second, and the velocity going back up again is 3.62 meters per second. Now at that point you should be going red alert, red alert, red alert, red alert. You haven't worked out your direction, mate. You've got to work out your direction. So whenever you draw a diagram, remember the whole 3D thing, draw your diagram, what is direction is positive, and then you can write your data. I've jumped into data, haven't defined my direction, so I'm already making a nice little mistake right there. So why don't we choose up as positive, same as we want to stay above the ground, then down is going to be negative, which means that my initial velocity as it's coming in should actually be minus 6.2. And as it bounces off the floor, it's now going to be plus 3.62. Okay, that's all looking good. And 4.2, reading the question again, calculate the magnitude of the impulse of the net force applied to the ball during its collision with the floor. Calculate the magnitude of the impulse of the net force applied to the ball during its collision with the floor. So we dive straight into formulas. Let's have a look here. This is our impulse formula. Oops, sorry. You can leave that as that's what impulse is given. As I said, it doesn't have its own letter, so you can just keep it like that. Or delta P is also fine. Let's put the details on the other side, because those are the things that we actually know, looking at the stats and facts that we've got on the right hand side. Let's sub it in. Mass is 0.15. You can in fact put these two in a bracket because the mass is the same in both cases. Vf is 3.62 minus 6.2. Okay, don't forget the double minus. And when you plug those into your calculator, uh, 0.15 times by 3.62 minus 6.2 equals 1,473. Now, units I didn't talk about previously, so you can label it impulse or you can leave it as F net delta T, that's absolutely fine. We can just use the kgs meters per second because we're dealing with momentum, it's the same thing. Or we can use an alternative unit, which is kind of more appropriate for impulse, based on these two quantities. Force is measured in newtons, time is measured in seconds. Newton seconds, not newtons per second, but Newton seconds. Okay, NS. Cool, that is the impulse experienced by the ball. Okay, so that's a little example. You've got another one or two to work through in your questions and your notes. Let's move on to conservation of momentum. So, again, a very common question with momentum is they love to get you to state what the principle is. So, what is the law of conservation of momentum? There's various different ways that you could do it. The most concise way, and the best way that I would recommend it, is the total linear momentum within a closed system remains constant. Okay, so that again, the total linear momentum within a closed system remains constant. Okay, write that one down. Let's have a quick look at where you would go with how to apply that. I think you've probably done many a question on this one. It's not hard at all, but it's meticulous. You have to be very careful that you don't lose values along the way, because there's quite a few of them. And in particular, watch out for the tsotsi that we've mentioned before, which is the minus sign. Direction is imperative. So you typically start your calculations with some kind of statement that kind of summarizes the law of conservation of momentum. Total initial momentum equals the total final momentum. And then you get into the details. Let's do that in the context of a question. So there's the M1 V1I and the M plus M2 V2I and all that kind of thing. Let's have a quick look at, it's the November 2011 paper. Question number 4. 4.3, they've asked us exactly what I said. State the law of conservation of momentum in words. And 4.4, we're just going to jump straight in there. Basically what we've got is we've got these two vehicles coming at each other. We've got a thief running away in a car of mass 1,000 kgs, going at 40 meters per second, colliding head-on with a truck, 5,000 kgs, moving at 20 meters per second. They collide, and after the collision, they move together, and we can ignore friction. And what we've got to do is calculate the velocity of the thief's car immediately after the collision for 6 marks. What a bonus. Okay, so let's quickly run through those facts. I'm not going to draw too fancy a picture, but pictures are always helpful. Let's put it up here. So here's the thief's car going along at 40 meters per second. Okay, called X, just for our reference. And then the bigger truck, whoa, weird truck, okay, is going along at 20 in the opposite direction. And we can call that Y. Boom, they're going to crash, and then after the collision, they're going to be stuck together. That's a mess. Anyway. Okay, so we are going to work out who's going to win and so on. We know that this one is 1,000 kgs. The mass of the car is going to run in different colors, so you can sort of see what's going on. And this one's going to be 5,000 kgs over here. Okay, and you'll probably guess which way things are going to go, but at this stage I'm just going to put a question mark as to what the velocity is going to be afterwards. We know that they're moving together, so the velocity of the thief's car, which we've been asked to find, is the same as the velocity of the truck. So this is one of those questions where it's together, it's apart before, together after. So then what we do is just say M, I've used X and Y, MX, VX initial, plus MY, VY initial, is going to be equal to their combined mass, mx plus my, both traveling at the final velocity. Okay, so that's still in algebra form, but it's detailed out more specifically what the law of conservation of momentum is. Sorry, that should be a bit more central, but that'll do the job. Now let's start subbing in some values. We know that the mass of the thief's car was 1,000. Their velocity, now again, be careful, I always forget this. Don't you forget that. Okay? The all-important thing of direction. Okay? So I'm going to give the thief a little bit of positivity, but it's not going to last long, I'm afraid. So let's have a look. Plus 40 is his velocity, their velocity, and the mass of the truck going at minus 20. Okay. Combined 1,000 plus 5,000, and that's the velocity that we've got to find. Okay. Let's do some substitutions and so on. These are not too hard, so I wouldn't be too worried about doing those calculations. Sometimes when there's squares and all sorts of complicated things, I'd recommend actually just keep things in their raw units. Maybe let's just do that to teach you good principles of calculations. Keep everything in its raw form until you get to the final answer. So all we want to do is get VF on its own, basically just bringing those other things on down to this side. Save myself a little bit of time. I'm actually just going to do this. Take that and put it down here. Okay, that's perfectly acceptable working, which means I can go straight to VF. Calculator. Here we are. So we need a fraction, and we're looking at 1,000 times by 40 plus 5,000 times by minus 20, and that's all over 1,000 plus 5,000 equals minus 10. There we go. Which does make some sense because the truck is bigger, and so it would end up, it's not a surprise that it ends up pushing the thief's car to the left. So minus 10, let's put that in a correct format for the final answer, 10 meters per second to, does it? Yes, so we have got a diagram that we're working on, so we can refer to it and say to the left. Okay. So that's the kind of question that you'll get with conservation of momentum. For the sake of time, I'm not going to go through the details of 4.5, which basically goes on to say, well, research has shown that forces bigger than a certain amount can cause a fatal injury. And then you have to just simply use impulse calculations, actually, because they tell you the time of the collision, 0.5 seconds, which already gives you a clue. And you can use that to find the force experienced by either of those vehicles and compare it to what the stats say and work out whether it's going to be fatal or not. Last thing on momentum, just before we wrap it up, is the whole thing of elastic and inelastic. What constitutes an elastic collision and an inelastic? Well, it's actually quite straightforward. Elastic collisions are where kinetic energy is conserved, and inelastic ones are where it's not. In reality, there's hardly any elastic collisions at all. Most collisions are inelastic. Energy gets lost somewhere along the way, but you have to show it. You have to show it in the form of a calculation. And again, it's fairly easy marks to give you an idea of how we would do it. I'm not going to do it in complete form, but just to show you the approach so that you can get onto the right track if you're asked to do that. This example, the thief and the truck, to saying, well, is this a collision elastic or inelastic? We can't say that the kinetic energy before is equal to the kinetic energy after because we actually don't know. So you can't write it all out as an equation like you do with momentum. But what you can do is say EK before equals EK of X plus the EK of Y. And then you can just sub in the values that we know. Well, let's keep it in algebra to start with. So half mv squared for both vehicles, half of 1,000 times 40 squared plus half of 5,000 times minus 20 squared. As you can see, the minus doesn't really make a difference because it's squared out. And then you work that all out. I'm not going to bother to do that. That would give us the before. Then you do the same thing for after. I haven't got enough room on the board, but I'd probably do it on the right-hand side. If you've got big writing and you fill up the whole page, then you can do it underneath, doesn't matter. Then you work out what it is before, work out what it is after, and then just simply compare the two at the end and say, if they are equal, it's an elastic collision. Kinetic energy is conserved. And if they're not, which is probably what you're expecting, then you can say it is an inelastic collision. And that pretty much wraps up momentum. Good luck. Have fun.